Alright, so I'm back and we are talking about cholesterol biosynthesis, and we just got to a point where we had HMG-CoA reductase and we generated this molecule known as mevalonate. Now mevalonate is our precursor for building our isoprene units, and so what we have to do is we have to use the enzyme mevalonate 5-phosphotransferase. That is an enzyme that takes ATP, transfers a phosphate group onto mevalonate to make this phosphomevalonate. Okay, now this begins the process of adding this PPi tail. Anytime you see PPi, that is an inorganic pyrophosphate molecule. You should think about that basically as looking like this: OPO, PO, 2 oxygen, double bonded oxygen, double bonded oxygen, oxygen, oxygen. So basically what we're doing is we're trying to add this whole thing on there. But this is a multi-step enzyme, or this is a multi-step process. The first enzyme, mevalonate 5-phosphotransferase, is going to generate our phosphomevalonate. Now, one thing that I'd like to kind of put as an aside here is we were just talking about HMG-CoA reductase, and that is an enzyme that is commonly used or targeted for reducing cholesterol. So whenever you think about this cholesterol biosynthesis pathway, I want you to think about every single one of these enzymes arguably would be a target for, well, inhibiting the production of cholesterol. With that said, though, if you're going to target this enzyme right here, mevalonate 5-phosphotransferase, well, you got to think, what would your inhibitor look like? Well, if it's a competitive inhibitor, then it's going to look like one of the substrates. Well, one substrate is mevalonate, the other substrate is ATP. Now, if you generated a inhibitor that looked exactly like ATP, would that really be an effective drug, or would that be an effective treatment for this enzyme? Yeah, probably would. Would that be an effective inhibitor for any other enzyme that uses ATP as well? Probably. So that might not be necessarily a good target. But if you were able to make something like mevalonate that you couldn't transfer a phosphate group to, maybe that would be an effective competitive inhibitor. But moving on. Okay, so we have this phosphomevalonate where we have our single phosphate group. Now what we have to do is we have to again add a phosphate group to it. So we've got our phosphomevalonate kinase. And so a kinase is going to transfer that phosphate group. We were talking about a phosphotransferase previously. Now we're talking about a kinase. We're taking ATP, we're transferring our gamma phosphate, our third phosphate in that chain, onto make 5-pyrophosphate mevalonate. So carbon number 5 has a pyrophosphate molecule, thus completing the production of our pyrophosphate tail on our mevalonate molecule. Okay, so once we've generated our 5-phosphomevalonate, what we can do is then go on to actually decarboxylate this and make isopentyl pyrophosphate, our IPP molecule. This is one of the isoprenoids that we're looking for, isoprene units that we're looking for synthesizing. The enzyme that does that is 5-PPi-mevalonate, 5-PPi-mevalonate decarboxylase. This removes our CO2 to form our isoprene unit. So we had HMG-CoA, and what we did to that was we converted this to mevalonate, and then that mevalonate, what we did was we added 2 PIs to make our 5-pyrophosphate mevalonate, and now what we did was we decarboxylated it, and all of a sudden we have IPP. This molecule right here is super important. We know that it's super important because we're talking about it in the context of cholesterol biosynthesis, but it's also important for, well, everything else that isoprene units are going to be involved in. One of those things is that we can use IPP for synthesizing different pigment molecules like carotenoids, so like beta carotene and everything like that. Obviously we don't do that, but this question right here, how does ATP fit into this reaction? Well, we have ATP as an input. We are decarboxylating 5-pyrophosphomevalonate what we are doing is we're using that high energy phosphodiester bond of ADP and PI, or that exists between two of the phosphate groups. We're going to break that in order to drive the decarboxylation. So we're not doing any sort of phosphotransfer or anything like that. All that we're doing is we're taking I'm just going to make P, P, P. So there's our ATP molecule. We're breaking this bond right here. We're using the energy from breaking that bond to break this bond right here and remove that CO2 molecule. Okay, so that's how ATP fits in there. Now, what that means, that we're coupling this hydrolysis of this phosphodiester bond with the removal of a CO2. It's kind of like the opposite of a ligase. A ligase is an enzyme that we're going to use ATP hydrolysis to make another bond. In this case, what we're doing is we're using ATP hydrolysis to break a bond here. All right, so hydrolysis of ATP drives long chain of otherwise unfavorable electron transfers. So one case is that we've got, as that's displayed, we've got our ADP molecule right here with our third phosphate group indicated right here. What we're going to do is transfer some of these electrons so that we can break this phosphate group, take this hydroxide group off of our 5-pyrophosphate mevalonate so that we can then decarboxylate and remove this CO2 from that 5-pyrophosphate mevalonate in order to make isopentenyl pyrophosphate. Okay, so that IPP is what it's commonly known as. That molecule is our first isoprene unit that we're going to be concerned with. Okay, now what we've got is we have IPP, isopentenyl pyrophosphate, that can be isomerized to make dimethylallyl pyrophosphate, or DMAPP. So IPP and DMAPP. Both of these are 5 carbon molecules. All that matters and all that differs about them is the placement of that double bond. Okay, so by going through this process, we basically have 2 isoprene units ready to work. Now, we're going to be able to use those different isoprene units, which have been highlighted right here. We're going to be able to use them to go in these different directions. But remember, what we talked about previously was we talked about the HMG-CoA reductase as the first enzyme or first committed step to isoprene biosynthesis. So at this point, we're getting into cholesterol biosynthesis, but all that we've really talked about is isoprene biosynthesis. So in the next video, we'll get into cholesterol biosynthesis a little bit more, but for the time being, thank you very much and have a good one.